All right, now it's time to start talking about how we're going to idealize these structures and structural elements that we just talked about. Why do we idealize structures into a model? Well, we use simplified models, or we use models, I guess. Right? We use models to simplify the analysis of a real world structure. Right? We say, okay, we're going to take that beam, we're going to make it a line, we're going to, all that. We how take a real life structure and simplify it a little bit to make it easier to model. So, for instance, here's a cantilevered beam on a column with a hanging load. Maybe there's an equipment hook. So, okay, let's see. I'll take my column and I'll make it a line. And I got my beam attached to it and I'll make it a line. And I'll put my little force. But the question is, what do we do at the joints? Right? So we got to figure out how to model these joints. Similarly, if I look at a slab across some girders, right? If I look at it in plan, here's my slab. Let's see, I've got some joists. Well, the joists I can kind of say they're like a beam, right? They're acting as a beam. So I can make my joists, right? A line. My girders, right? This is the girder that the joist rests on. It's just a big beam. Okay, there's a line. And then if I look at it in plan, right, I have my joists, and I have my girders, and they're resting on columns, right? You just take the elements of the real world structure and say, what could I use to model that element? So talking about the supports and joints and how we model them, I would ask, in what ways can a structure move or not? Like, if we're measuring movement or not movement of a structure, what exactly are we looking at? Basically, we like to measure the movement of a structure two different ways. Displacement denoted by a delta, and that is measured in inches, right? A length measurement. And we also measure rotations at a specific joint, which is denoted by a theta. So that's an angle. So let's say movement at joints, right? It's how we measure or supports. It's how we measure the movement of a structure. We look at the movement at joints or supports. And does it displace, which is something you measure in length, like inches. Hopefully not feet. I hope your buildings aren't displacing by feet. Or rotations, an angle. Is my element rotating about a joint or a support, right? Conversely, what holds something in place? Those would be our reactions, right? The reactions at joints and reactions or, what do I say? Reactions or forces at joints, supports. Those reactions or those forces are preventing the movement of a structure. And typically we measure that in force, right? Some type of, which is in units of force, right? Kip, Newton, or moments. Right, Kip feet, Newton meters. So we measure movement or not by displacing with delta, and that's a length measurement, rotations, theta, that's an angle if something is rotating about a joint or a support. And then we can measure the force preventing that movement, the reaction preventing that movement. We measure forces and we measure moments. So let's look at one of the simplest support. This is a roller support. So let's say I apply a force in the x direction, right? Let's say px in the x direction. What happens to this beam? Well, it deflects in the x direction. In all of these, I'm using x and y. We're going to stick to two-dimensional right now. Because it's easier. So if I apply a force, that beam is moving horizontally. So that means that roller is not doing anything, right? So if I look at my different is there movement in the x direction at that roller support? Yes, we don't know what it is, but yes, there's a value. Right, now let's see if I apply a vertical load. Right there. What happens? Well, right, I'm going to have a deflected shape like that. Kind of like a seesaw, right? So if I look at the support, do I have any deflection in the Y direction? No. It's pivoting about that, right? It's rotating. So the next question, do I have rotation about the Z-axis? Right? This is the Z-axis out of the plane. Yes. Right? There we go. It's more like that. So yes. So at a roller support, the only movement that is constrained is my deflection in the Y direction. The beam can move horizontally and it can rotate about the Z-axis. Now if I talk about reactions, right? There's a force in the X direction, a force in the Y, a reaction in the Y direction, and a moment about Z. Is there any force preventing that deflection in the X direction? No. So there's no reaction there. Is there a reaction constraining the deflection in the Y direction? Yep. So it's some value. And is there any moment preventing the rotation about the Z-axis? Nope. So the only unknown that I have at a roller support, the only reaction that I have is a vertical force. There's no horizontal force preventing movement in the horizontal direction, and there's no moment preventing rotation about Z. Right? You notice I have zero, or I have some type of movement in the X direction, so I have zero reaction force. I have no movement in the Y, no displacement in the Y direction, so I have some kind of reaction, but I have an unknown amount of rotation, so I have no moment preventing that rotation. Now let's look at a pinned connection. Here I have a beam connected to a column, but the only part of the beam that's connected is the stem, or the web, I'm sorry. The web of the I-beam. So again, let's say I apply a horizontal load. If I look at the moment right, or at the deflection right at the support here, is there any displacement in the horizontal direction? No. So compared to a roller, now a pin connection constrains in the horizontal direction. If I apply a vertical load here, what will my displaced shape look like? Something like that, right? I don't know. So now, if I look at the support specifically, is there any deflection in the vertical direction? No. Let's see. However, is there rotation about Z? Yup. So a pin connection prevents displacement in the X and Y direction, but it does not prevent rotation about Z. Similarly, so now a reaction. So what is preventing that displacement? A reaction force in the X direction, a reaction force in the Y direction. However, there's no moment preventing rotation, so there's no moment reaction. So a pin connection versus a roller, you have one more constraint in the horizontal direction. The roller only had the constraint in the vertical direction. Now you have constraint in the X and Y direction. So you have reactions in those two, but you don't constrain any rotation. So there's no moment preventing that rotation. Now, if we're starting to look at a fixed connection, now not only is my web connected by this bolted angle, but my flanges are also connected. So again, let's see if I apply a force in the X direction. Is there any deflection there at the pin support? Nope. So my deflection in the horizontal direction is 0. If I apply a vertical load out there, what happens? Well, these bolts to my flange are preventing rotation, right? So there is no displacement in the Y direction, and there's also no rotation, specifically at the support, right? So a fixed connection means no displacements and no rotations at the support, at the connection. What's preventing that displacement and rotation? A horizontal reaction force, a vertical reaction force, and a moment. All right. Guess I should go back and, right, we have our horizontal or vertical reaction for a roller. This is what I get for not looking at my notes. Here we have a vertical reaction and a horizontal reaction. That's for a pinned connection, right? But we don't have any moment. And then if we look at a fixed connection, we have a horizontal reaction, a vertical reaction, and a moment reaction. Okay? So those were all for kind of like supports, but now what if I'm joining two different beams or two different columns, right? Well, let's see. If I apply some type of force, let's say I'm applying a tension force in the horizontal direction. Say I apply a horizontal tensile force. If I'm looking over here at the support, is there going to be any horizontal displacement? No, because this other beam is holding it in place. It's providing stiffness and constraining that movement. Right? There's some tensile force being transferred at that joint. Let's say I apply a vertical I should have called that P. Let's say I apply a vertical force at both of them, or even at one, but let's say, right? What would happen? Well, I would have displacement like that. So if I look at here, at the center of the support, is there any movement in the vertical direction? No. But is there rotation? Yup. Sorry. There's some type of rotation. So I'm going to have some reaction preventing that vertical movement. But I'm not going to have any moment being transferred preventing that rotation.
So it was in your office. My Kindle was in your office.
Molly, I told you to be quiet. So if we have a vertical reaction preventing that movement in the vertical direction, but we don't have a moment being transferred. One place where you especially might see a pin joint is if we create a plastic hinge on purpose. That means that we it might actually also happen on accident, but we've weakened like a beam so much due to a really high stress that it behaves plastically and can freely rotate and displace. So now if I were to like apply a load, right, a distributed load, it would hinge. Let's say it was supported on either end, it would displace like that. We create a hinge. That's a pin pin joint or a hinged joint. Similarly, we can have a fixed joint, and you probably have guessed at this point what happens at a fixed joint. Let's say we apply a horizontal load. Is there any deflection over here? Or forces being transferred? Right? Is there any movement at this horizontally at the joint? No. If and what's holding it back? A reaction force or a force that is going to end up being transferred into the beam that it's connected to. If I apply a horizontal, right, we're probably going to have some, oh, no. These fixed plates right here are going to prevent rotation, right? So I have a displaced shape that looks like that. So if I look specifically at the joint itself, I don't have any vertical movement and I don't have any rotation. And what's preventing that is a force that's going to be transferred to the beam next door and some type of moment. So similarly to a fixed support, I have no displacement and no rotations. And no, and I have forces and moments being transferred. So this would be, if you connect two beams like this, it's basically analogous or equivalent to a continuous beam. This type of joint is often found at column splices. You can only make columns so tall before it's prohibitive to move them from where they're made at the mill or the fabrication shop to your site. So if you're building a building taller than, a couple stories, you're going to have a splice to join your columns, and you make a fixed joint there so that the column will act as one whole column that's like 4 stories tall instead of 2 columns that are 2 stories tall each. And finally, I'm going to talk about what happens if you have something that's between a fixed and a pin joint, right? If you recall, at a pin joint, we have no deflections, but we have rotation. If you have a fixed joint, you have no deflections and no rotations. What if you had something between that? It's called a torsional spring. And really what we're talking about is that the fixity of the joint or the fixity of the support constrains a little bit of rotation, but not equivalent to zero rotation, right? So a torsional spring constrains rotation. Let's say I applied a vertical load here and a vertical load here. If I had a pinned joint, then I would have a displaced shape kind of like that. But if I have a little bit more fixity, additional rotation constraint, then it would look more like that. It wouldn't be able to rotate quite as much, right? Right, this is my torsional spring displaced shape, and this dotted line is my pin. Versus if I had a fixed beam, right? A fixed joint, it would look a little bit like that. I would have no rotation, right? So this is my theta for a pin joint. This is my theta for a torsional spring. So it just constrains the rotation a little bit more than a pinned, which is 0. And it's denoted often by a spring, right? We have a pin and then we add a spring onto it, and it has a K constant, which is the spring constant. Right, that spring constant that is preventing the rotation. If K was 0, that would mean there is no rotation constraint, which would essentially be a pin, right? What I mean to say, if K equals 0, if K was infinity, then it would be preventing all rotation, and it would be analogous to a fixed connection. So, like I said, this torsional spring is used for adding rotational rigidity, constraining the rotation to a joint or a support. Now I'm going to summarize what we've talked about today and talk about how we draw them as an idealized symbol when we're modeling. If I take a roller, right, that was the one, well, we'll remind ourselves, right? If I look at a roller support, that looks like a little ball or a triangle on some rollers. That's, if you see that, that means it's a roller support. If you recall, roller, the only movement it constrains is movement in the vertical direction or Y direction. Consequently, the reaction preventing that movement is a force in the Y direction. And that means the only unknown reaction at that support is 1. Because we know that the force in the X direction and the moment about Z are 0. So we only have one unknown in a roller support. If I look at a pin support, it looks like a little triangle. A pin means it can't move in the horizontal direction and it can't move in the vertical direction. So I have a horizontal reaction force and a vertical reaction force. 1, 2. 2 unknowns. If I'm talking about something that's a fixed reaction, remember that was where I had my flanges attached as well as my web, as one example, right? Then I draw it like that. I guess if it was a column, right, it would be like that. Fixed connections means it can't displace in either direction and it can't rotate. So that means I have a reaction force in X and Y and a reaction moment about the Z axis. 1, 2, 3. If I look at a slider connection, you know, this, if you look at it, kind of, it's like something that can go up and down, but it can't go side to side and it can't rotate. That's drawn as that. Kind of looks like a cross between my roller and my fixed. So that means it can't go horizontal, at least drawn in this configuration, but it can go up and down. So it can't go horizontal and it can't rotate. And so it has a horizontal reaction force and a moment reaction force. And we have 2 unknowns. If I want to model rotational rigidity of a pinned connection, so you know, like something between a pin and a fixed joint, I'm going to have my torsional spring. I'm going to draw it like that. This means it can't rotate or it can't displace in the X and Y direction. It's going to have some type of rotation, but that's going to be a rotation and it's going to have a horizontal, vertical, and reaction force and a moment preventing that full rotation, similar to a pin, right? That moment is constraining the rotation that just a plain pin would allow. So 1, 2, 3. And pardon me. So if that rotation and the moment preventing full rotation, they vary with a spring constant. So this is a chart summarizing all of the different supports. Right, roller, pin, fixed, a slider, and then a torsional spring. There may be some others in the book. If you're looking at different types of joints, if we have a hinged or a pin joint in a beam or a frame, we're going to draw that with a big old dot. That's connecting two beams or connecting a beam and a column. What movement does this constrain? Deflection in the X direction and deflection in the Y direction. So we're transferring forces in the X direction and the Y direction. 1, 2 unknowns. Sorry. If I have a beam, beams are not vertical. If I have a beam that's connected to another beam, right, might be kind of, I don't know, like that. Not a circle. But really you don't see that because it'd just be a continuous beam. But if you're looking at a frame, draw a little triangle in the corner. It's basically saying, hey, I beefed up this connection and now it's a fixed connection, right? And it's constraining deflection in the X and Y direction and rotation about Z. So I'm transferring forces in the X and Y direction and a moment. 1, 2, 3 unknowns. And finally, I have my torsional spring. All right, if I'm looking at like a frame, I'm going to put a little spiral right there saying, hey, there's a torsional spring here. Again, it's similar to a pin, so we have deflection in the X and Y direction being constrained and some type of rotation being constrained, but we don't know what it is. Similarly, forces in the X and Y direction and some type of moment are all being transferred at that joint. So 3 unknowns. And joints are considered to have compatibility. Compatibility, meaning the deflections and the rotations at a joint are the same for the connecting members. If you have 2 beams that are connected by a pinned or a fixed joint, they're both gonna, at that joint, they're both gonna deflect vertically the same and horizontally the same if they deflect. And they're gonna rotate the same if those are allowed. So let's take a look at a couple of different connections and think about what type of idealized connection or support or joint we would use if we were modeling them. See, look at number A, letter A. Right, we have a beam where the web and the flanges are all connected to the column by welds. So if the flanges are connected, then we're restraining rotation. And I would call that, what would you call it? Give you a minute. Fixed connection, right? Looking at number B, letter B, it's definitely being constrained vertically. Doesn't look like it's being constrained rotationally. Not sure about the horizontal, so I would probably, that looks like it's a roller. But if it's like, let's say it's bolted right here or something, then that would be preventing horizontal movement. So that would be a pin, right? Kind of looks like it's just laying on top of that support, but if there's any type of connecting element, that could be a pin. So letter C. Let's see, if we push it horizontally, could it move? Yep. If we applied a load, could it rotate? Yep. So we're looking at a roller. And finally, D. See, they can't deflect horizontally, they can't deflect vertically, but looks like they could probably rotate about this hinge, right? This looks like a hinge. So I'd call that a pinned or hinged connection. So if we go back up to our drawing, let's see, how would we model this? So we've got our beam And our column, how is this column connected to the ground? Can't go up and down, can't go side to side. Can it rotate? Probably not. So this is probably a fixed connection, right? So I would draw it like that. Now if I look at the beam to column connection, can it rotate? Not really. And it's going to be constrained horizontally and vertically. So I'd call that a fixed connection or a moment connection as well. So if we go back and look at how we draw that, it would be a little triangle right there. So that's how we would draw this structure as an idealized model. And with that, we've wrapped up what is a structure. And next up will be what is a load. Be sure to write down any questions you may have. Thank you.